Hello everybody, in this video we will analyze this circuit in which we have basically an inverter, analogical inverter, analog inverter based on a BJT NPN transistor. So we have here our input with this offset of 2.5 volt and amplitude peak to peak 4 volt. So we have between 0.5 and 4.5. So we have this polarization and signal. Then our base resistor, the transistor, we take the output between collector and emitter, then we have 1K resistor here and this 7 volt battery for polarization. So we implement this circuit on the protoboard. So I have here basically my 1K resistor between collector and 7 volt battery. Then I have my 200K resistor between base and signal, and then the emitter is connected to the both negative terminal of both batteries. So I have my ground here. So on this side, the base side, I have my function generator with an offset of 2.5 volt, 4 volt peak to peak, and 1 kilohertz frequency of my sinusoidal waveform. On the other side, on the collector, I have my fixed battery of 7 volt, almost 7 volt. It's okay like this. So now I want to connect here my oscilloscope so that I can see this trace. I expect to have input and output like this, so I am amplifying and inverting. In this picture is like amplification 1, but just for understanding. So I have my input and output, they are inverted, and also I can plot one channel as a function of the other, and by varying the offset and amplitude I will see all the transfer function of my inverter with this slope from theory and this off region and saturation region that I know from my theory. So I connect the two channels of the oscilloscope. Channel 1 between the base, let's say the input voltage at the base and ground, which is the emitter, and channel 2 between the collector and the ground. So basically I connect channel 1 between this point and this point, and channel 2 between this point and this point. So this is my channel 1, which is actually my voltage centered more or less at 2.5 and between 0.5 to 4.5 more or less. And on channel 2 I have my output voltage, which is the input inverted and with some bias point on top, some polarization bias obviously. So we have this figure here, which is actually our inverter, and if I, for example, I increase the amplitude of my signal, so here, for example, I increase the amplitude of my signal, I see that I'm cutting my output waveform because I go out from the linear region here. We'll see this also. And on the same let's say argument, if I change my offset, so if I change my offset, I move my bias of the input, I will have some clipping of the output signal. I will lose my trigger maybe, yes, exactly. So I will move this a little bit up, and again, if I'm moving, I will finally have to clip, like now, exactly, I'm clipping my output signal. Anyway, so we go back to the linear region with the previous parameter, like it was 4 volt, so no, it was like offset of 2.5, more or less. Anyway, I can see this on the oscilloscope, my trigger is lost again. So here I have my linear region. And if I want to see this on a different point of view, yes, this is the XY display. So this line is actually this line here, this slope. And I can see a bigger range if I increase my amplitude. So I increase my amplitude and I increase my range. If I want to center this, I will change my offset. And so on this side, yeah. So basically, this is what I have on the XY display. And if I want to see this on time, I see my input signal, okay, maybe my input signal, okay, like this, and my output signal, which is clipped. Okay, so the clipped region corresponds to this flat region, and this one is the linear one. Thank you for watching. I hope this video could help your understanding of this subject.